Okay, welcome to 2.5. Today we are going to use technology to approximate roots of polynomial equations. And our technology will be our graphing calculator. This, in many people's minds, would be the best graphing calculator on the market right here. It's expensive, but if you're going to go off to college and continue to take mathematics, it's going to be a great tool for years to come for you. All right, and so we can easily approximate the roots of any equation with our graphing calculator, and the roots are simply nothing more than where the graph crosses the x-axis. Like this red cubic right there looks like it has a root somewhere between -2 and -1, another root right at about 1, and then another root at about probably 1.5. Now I just looked and approximated, but your calculator will give you much more accurate approximations than we just did with our eyes. But first, we must go old school and approximate the roots analytically. All right, and to do that, we use what is called the location principle. The location principle. So if p of x is a polynomial with real coefficients, so I'm going to draw a coordinate plane, and I'm going to put a random part of a random polynomial on this coordinate plane, something like that right there. Maybe that's part of a cubic. All right, and a and b are real numbers such that p of a and p of b have opposite signs. So I need an a and a b on the x-axis, and the root's going to be somewhere in between a and b. And then p of a would be this y value down there, and p of b would be this y value up top right there. P of b, p of a. And they have opposite signs. In this case, p of a is negative and p of b is positive. Then between a and b, remember this symbol, there exists at least one real root r. So there's my r right there in this case, of the equation p of x equals 0. Now the reason the location principle has to be true is because polynomials are continuous. So if the output of a polynomial is negative, and then it's positive, it must cross the x-axis somewhere in between in this case, a and b when you graph it. That's where we have our root right there. The location principle is actually how roots were located before the graphing calculator. It was tedious but necessary. Now, most of the time we try to solve without these approximations, but we cannot solve every polynomial equation, and that's why we needed the location principle. Alright, so to apply the location principle, we use a tool called the bisection method. Alright, and with that, finding a neighborhood with a 0. Well, I've given you the graph over here of what looks to be a cubic, at least in this window, it looks cubic to me. And do you guys all agree that this cubic has a root somewhere between 2 and 3? So if I was going to use the bisection method to find that root, I would actually begin with an interval from 2 to 3. Now just for some practice, I'm going to make that interval here a little bit bigger. So I'm going to start with an interval of 1 to 3. And yes, this is pre-technology and it was tedious. Alright, but the reason I'm choosing the 1 to 3 is because the function, well, p of 1 is obviously negative and p of 3 is obviously positive. So there is my closed interval from 1 to 3. Now that's interval notation. Know the difference between brackets and parentheses in interval notation, but this is the notation equivalent to the double inequality. 1 is less than or equal to x, and x is less than or equal to 3. Now, what is the midpoint of this closed interval right here? It would be 2. And now I'm going to check my outputs. Let's go ahead and plot p of 2 So let's put a point on a curve about right there. Now, obviously, P of 2 is negative and P of 3 is positive. So let's talk outputs, P of 2 and P of 3. Okay, oh, we're using F for function. Okay, so F of 2 is, well, that's a negative number, so it's less than 0. And F of 3 is, that's going to be a positive number. It's greater than 0. So now I get to decrease my interval. I'm cutting it in half. And over here, I'm going to use an open interval. I'm going to say there has to be a 0 in the open interval between x equals 2 and x equals 3, 2 and 3. Again, know the difference between an open interval and a closed interval. This open interval means 2 is less than x and x is less than 3. So now let's bring this open interval and write it over here as a closed interval. This is the interval I'm working with now. 2 is less than or equal to x, and x is less than or equal to 3. And what's the midpoint between 2 and 3? Be 2.5, or if you want to use a fraction, you could say 5 over 2. Now, let's find P of 5 over 2. Well, that would be right about there. And obviously, P of 5 over 2 is negative, so now I'm going to do my outputs again. And I'm going to use the 5 over 2 and 3 as my inputs. So F of 5 over 2 is what? It is less than 0. F of 3 is what? It is greater than 0. So now I know the 0 has to be in between those two x values. See, my interval is getting smaller and smaller. We just cut it in half again. So the 0 is in the open interval from 5 over 2 to 3. So now let's make this a closed interval over here. And now what's the midpoint between 5 halves and, how about I call that 6 halves? Well, that would be, could I think of that 5 halves and 6 halves as what? 10 fourths and 12 fourths? So wouldn't that be 11 over 4? Let's see if that's what I did there. Yeah, look at that, 11 over 4. A little practice with fractions today. Now, where is 11 over 4 on my graph on the x-axis? Well, think about that. That would be what, 2 3/4? That would be right about there. And we're still negative. So now my interval is f of 11/4, or my outputs, f of 11/4 and f of 3. And f of 11/4 is less than 0. F of 3 is still greater than 0. So now my conclusion, the 0 has to be in the open interval between 11 over 4 and 3. Now let's practice with fractions a little more here. This open interval now becomes my closed interval that I'm going to check over here. And now think about how I do this for the midpoint. 11 over 4, and could I go 12 over 4? And that would be, well, 11/4 is 22 over 8. 12/4 is 24 over 8. So wouldn't the midpoint have to be 23 over 8? Do you guys see how I'm doing that arithmetic? This is kind of cool. And 23 over 8, now that's going to be kind of hard to think about in this little interval right here. But so I'm going to make it a mixed number here. 8 goes into 23 2 times, so that'd be 2 and 7/8. 2 and 7/8 is going to be slightly above, well, I should say f of 2 and 7/8 is going to be slightly above the x-axis. So now my outputs, I'm concerned about these two outputs right there. So I'm going to go the output of the f of 11/4, which we said above, is less than 0. And then if you look at this carefully, f of 23 over 8 is greater than 0. All right, so now I know, and I'm in a neighborhood close enough for my approximation right here. I know that the 0 needs to be in the open interval, and I'm going to write this 11 over 4 a little differently so I can really stress how small this interval is. So do you guys agree that 11 over 4 is 22 over 8? And then 23 over 8. This root right there has to be somewhere in this open interval. And we could keep going and going and going to get more and more exact. But that would be a lot of arithmetic with a lot of fractions. All right, I hope you enjoyed that. So the location principle is valid but dated. We will mainly use our graphing calculator to find the roots of complicated polynomial equations. So let's start with, and we're going to finish with this actually, we're going to solve the cubic equation x to the third minus x squared minus 5x plus 2 equals 0. Now, when you try to visualize this in your mind right now, a cubic has at least 1 and up to 3 zeros. Know the shape of your graph. So I focus on the leading coefficient of 1 that is greater than 0 and a cubic. So with this leading coefficient, aren't I going to start down in quadrant 3 and then go up and take a turn and another turn and finish up here in quadrant 1? So this cubic I'm picturing as looking something like that right there. Now, what do they mean at least 1 and up to 3 zeros? Well, depending on where this cubic is on the plane, the x-axis has to intersect the x-axis at least once. Maybe like that right there. Okay. Or here it intersects at 2 places. This is a single root and this is a double root. By the way, the first one was a single root. Or we could have 3 zeros right there. And these are all single roots. 1, 2, 3. So there's the possibility right there. So if I'm going to use my calculator, I need to know the general shape of my cubic. So I know I have a valid window. So I'm going to put this into my calculator as y sub 1. And I'm probably going to go zoom standard and see if I can see everything. And there it is. That looks like a standard window, and I can see 3 roots right there. So I'm ready to go. My calculator will find these roots for me. And all I'm going to do is go. Oh, by the way, there's where I'm going to put the roots up there. And I'm going to go second calc, and then on the calc menu, 2 is finding the zeros of one of these equations right here. All right, so now the first one. Now when I do that, second calc 0, my screen's going to come up to this graph again, and I'm going to be asked to move the cursor below the root and above the root, and only use your left and right arrows to do that. And then it's going to say guess. When I go left bound, enter, right bound, enter, guess. And guess what my calculator gave me? The first root is x equals -2. I write that as an ordered pair. -2, 0. Okay. Now, the second root, I'm going to do the same thing now. Second calc 2. And it's going to take me to this graph, and my answer is not showing yet. I have to go left bound, so I get my cursor to the left of that 0 and hit enter. Right bound, I move the cursor to the right of that 0 and hit enter. And then guess, I hit enter one more time. And I have this decimal, 0.38. I'll probably go like 0.4 there. Yeah, 0.40. And now I have one more root to find. Second calc 2, 0, one more time. And then left bound, hit enter. Right bound, hit enter. And remember to move your cursor on the curve, only use your left and right arrows. And then my guess, I hit enter again. And this x, or this root, is approximately 2.60. So that's how we use technology. A little more efficient than the bisection method, by the way. So I would like you guys to do 2.5, 1 through 12, and 15. Thank you, and have a great day.